Think a dual engine failure means certain disaster? Think again. Hollywood loves to show planes dropping out of the sky the second the engines go quiet, but that's just not how it works. A massive commercial jetliner is basically a super efficient glider. Losing both engines is one of the rarest things that can happen in aviation, like winning the lottery and getting struck by lightning on the same day. But even if it does happen, the pilots aren't helpless, and the plane doesn't just fall. It's an incredibly terrifying thought, but the reality is fascinating. Today, we're busting the biggest myths about what really happens if both engines fail on a Boeing jet, and the incredible safety systems that kick in. We're going to dive deep into the engineering marvels that keep you safe, even when things go catastrophically wrong. We'll look at everything from a tiny hidden propeller that saves the day, to the onboard computers that literally walk pilots through the emergencies step by step. Forget the movie scenes of chaos and screaming. We're going to show you the calm, calculated procedures and the layers upon layers of backup systems that are designed for this exact, super unlikely scenario. By the end of this video, you'll understand why pilots train for this, why engineers have planned for this, and why you can actually feel safer knowing what happens when everything seems to fail. This is the real story of survival at 30,000 feet. Let's get into it. So first up, the most obvious reason engines might stop: they run out of fuel. It sounds unbelievably simple, like forgetting to fill up your car, but for $1 billion aircraft, it's a whole different ballgame. This is called fuel exhaustion. The computers on these planes are insanely accurate at calculating fuel burn, and there are multiple redundant sensors in every single tank. Before every flight, the pilots, the dispatchers, and the ground crew all cross-check the fuel load against the flight plan, which includes tons of extra fuel for diversions, holding patterns, and unexpected headwinds. It's a system built on triple-checking everything. The other fuel-related issue is contamination. This is where water, dirt, or even the wrong type of fuel gets into the tanks. This is also incredibly rare because fuel is filtered multiple times before it ever gets near the aircraft. It's tested at the refinery, tested at the airport storage facility, and tested again from the fuel truck. Pilots will even perform a final check themselves, draining a small sample from the wing tanks to visually inspect it for any water or debris. So while running out of clean fuel can technically happen, the layers of prevention make it almost impossible on a modern Boeing jet. Okay, this next one sounds like it's straight out of an action movie, volcanic ash. And it's a real threat. When a volcano erupts, it spews a massive cloud of fine rock, glass, and sand particles thousands of feet into the air, right where planes fly. If a jet flies through this, the ash gets sucked into the engines. It doesn't just clog them up. The intense heat inside the engine's core melts the ash into a layer of molten glass. This glass then coats the turbine blades and other critical parts, starving the engine of air and causing it to flame out. It's one of the few things that can knock out multiple engines at once. But here's the thing. Pilots and air traffic controllers know this. We have an incredible network of volcanic ash advisory centers, or VAACs, all around the world. They use satellites, radar, and weather models to track these ash clouds in real time. This information is blasted out to every airline and pilot, and massive no-fly zones are created around the ash. Pilots are trained to recognize the signs, like a strange haze or the smell of sulfur, and to immediately turn away. So while volcanic ash is super dangerous for engines, avoiding it is a top priority in global aviation. Let's talk about Mother Nature's fury severe weather. We're talking about massive thunderstorms that can throw everything at a plane, including extreme icing and hail the size of golf balls or even bigger. When a plane flies through intense hail, it can physically batter the front of the engines, denting the fan blades and damaging the intake. In the most extreme cases, if the engine ingests a huge amount of hail and water in a short time, it can disrupt the airflow and combustion enough to cause a flameout. It's like trying to keep a bonfire going in a hurricane. This is a serious concern for pilots. However, Boeing jets are built like tanks to handle insane weather. The engines undergo rigorous testing, including having high-pressure fire hoses blast water and ice into them while they're running at full power to prove they can handle it. More importantly, pilots have incredibly sophisticated weather radar on board. They can see the structure of storms hundreds of miles away, identifying the most intense cores of precipitation and turbulence. Their number one job is not to fly through the storm, but to fly around it, navigating a safe path, even if it adds time to the flight. This is the one everyone knows about, thanks to Captain Sully and the Miracle on the Hudson. A bird strike. Now, hitting one or two small birds usually does nothing. These engines are designed to ingest a standard-sized bird and keep running without any major issues. But the nightmare scenario is a flock of large birds, like Canada geese, getting sucked into both engines at a critical moment, like takeoff. The impact of multiple large birds can bend or break the fan blades, causing a catastrophic failure of the engine's core. It's a pure physics problem: high speed, high mass, and delicate, fast-spinning machinery. Because this is such a known risk, especially around airports, a huge amount of effort goes into preventing it. Airports employ entire teams of wildlife biologists. They use a crazy variety of tools to keep birds away from runways, including trained falcons, dogs, propane cannons that make loud booms, and even recordings of predator calls blasted over loudspeakers. They manage the landscape to make it less attractive to birds, removing food sources and nesting areas. It's a constant battle between nature and technology, and these mitigation efforts have made dual-engine failures from bird strikes incredibly rare. Engines today aren't just mechanical, they're controlled by sophisticated computers. So what happens if the plane's entire electrical system just dies? A total electrical failure is another one of those almost impossible scenarios that engineers have obsessed over. In a modern Boeing, this would be like the power going out in your entire city, including every single backup generator all at once. The main engine controls, the fuel pumps, and the cockpit displays all rely on electricity. Losing all of it would be a huge problem, as pilots would lose the ability to control and monitor the engines. This is why there isn't just one electrical system. There are multiple, completely independent ones. You have the main engine generators, the APU generator, external ground power, and finally, a battery backup system. If one system fails, another one kicks in automatically. If a generator fails, the other engine's generator can power the entire plane. If both of those fail, the APU can be started. If all of that fails, there's a battery. And if the entire electrical system somehow fails, there's one more trick up the plane's sleeve, which we'll get to in a bit. The redundancy is staggering. We trust software with everything these days, from our money to our memories. But what if the software running the engines has a bug? A glitch in the Full Authority Digital Engine Control, or FADEC, could theoretically send the wrong commands to the engine, potentially causing it to shut down. If the same faulty software is running on both engine controllers, it could affect both. This is a terrifying thought, and it's a major focus for aircraft manufacturers and safety regulators. People worry about this a lot, especially with computers controlling more and more of the plane. This is why aviation software is probably the most scrutinized and tested code on the planet. It's not like an app on your phone that gets a quick update if there's a bug. The software goes through millions of hours of simulation and testing. Crucially, the FADEC systems often have multiple independent computing channels. Sometimes they even have software that was programmed by entirely separate teams to prevent a single human error from being duplicated. The level of verification, validation, and redundancy built into these systems is meant to ensure that a single software glitch can't bring down a plane. Even with the most advanced technology in the world, there's still a human in the cockpit. So we have to talk about the possibility of pilot error. Could a pilot accidentally shut down both engines? In theory, yes. For example, mismanaging the fuel system by turning off the wrong pumps, or mishandling a fire drill and shutting down the wrong engine, then shutting down the other one by mistake. These things have happened in aviation history, which is precisely why training and procedures have evolved so much to prevent them from ever happening again. Modern cockpits are designed around something called Crew Resource Management, or CRM. It's all about teamwork, cross-checking, and communication. One pilot proposes an action, and the other pilot must verify it. Checklists are king. For any critical action, like shutting down an engine, there is a physical, step-by-step checklist that both pilots must go through together. This forces them to slow down, think, and confirm that they are taking the correct action on the correct engine. This disciplined, methodical approach is the ultimate safeguard against a single human mistake turning into a catastrophe. Okay, so the absolute worst has happened. For whatever reason, both engines have failed, and the plane is now a 200-ton glider. The main electrical generators attached to those engines are no longer making power. This is where one of the coolest pieces of engineering comes into play: the ram air turbine, or RAT. The RAT is a small propeller, usually hidden in the wing root or the belly of the plane. When the computers sense a total loss of power from both engines, it deploys automatically, dropping into the fast-moving air rushing past the plane. As the wind spins this little propeller, it drives a small generator and a hydraulic pump. It doesn't produce enough power to run everything. The coffee makers and cabin lights are staying off, but it produces just enough to power the most critical things. We're talking about the essential flight controls, the captain's main flight display, and the communication radios. The RAT is the ultimate lifeline. It ensures that even with no engines, the pilots can still fly the airplane, navigate, and talk to air traffic control to coordinate a safe landing. It's the plane's life support system. While the RAT is providing immediate essential power, the pilots are already working on the next step, starting the Auxiliary Power Unit, or APU. The APU is a small third-jet engine located in the tail cone of the aircraft. You've probably heard its distinctive whine while you're boarding at the gate. Its main job is to provide electricity and air conditioning on the ground when the main engines are off. But here's the crucial part. It can also be started in the air. It has its own fuel line and its own battery for starting. Starting the APU is a key part of the dual-engine failure checklist. It might take a minute or so to spool up, especially at high altitude, but once it's running, it's a game changer. The APU generator produces way more power than the RAT, enough to restore power to most of the plane's systems, including more of the flight displays and hydraulic pumps. This gives the pilots a much better picture of what's going on and more robust control of the aircraft. It buys them precious time and options, making the job of gliding the plane to a safe runway much, much easier. So, the pilots have no engines, the RAT is deployed, the APU is starting, and there are alarms going off everywhere. How do they manage the chaos? They don't have to rely on memory alone. They have an incredible onboard computer system that acts as their co-pilot. In a Boeing, it's called the Engine Indicating and Crew Alerting System, or EICAS. On an Airbus, it's the ECAM. These systems are designed to be the ultimate emergency guide. The second a problem occurs, the EICAS immediately prioritizes the warnings. Instead of just a mess of flashing lights, the EICAS displays the exact problem at the top of a screen, like Engine 1 fail. But it doesn't stop there. Below the warning, it automatically displays the exact checklist and the precise actions the pilots need to take in the correct order. It tells them which switch to flip, which button to press, which system to check. As the pilots complete each step, the system updates, moving on to the next one. It removes the guesswork and the potential for panic-induced mistakes, ensuring the crew performs the right procedures methodically, even under the most extreme pressure imaginable. So, as we've seen, losing both engines on a Boeing jet is not the automatic death sentence you see in movies. It is an extraordinarily rare event, but it is an event that thousands of engineers and pilots have planned and trained for. From the multiple layers of prevention that stop things like fuel exhaustion and bird strikes, to the incredible backup systems that kick in when the worst happens. The plane itself is designed to be a stable, controllable glider, giving pilots time and altitude to work the problem. The ram air turbine provides instant life support, the APU acts as a powerful backup generator, and the EACAS system is like having the instruction manual open to the right page, guiding the crew through every single step. It's a symphony of redundant systems and procedural discipline, all designed with one single goal: to get everyone on the ground safely. The miracle on the Hudson wasn't a one-off fluke. It was the successful outcome of a system working exactly as it was designed to. Every time you step on a plane, you are stepping into one of the most resilient, over-engineered, and safest machines ever created by humankind. The odds of being in a situation like this are astronomically low, but knowing these systems exist should give you confidence. So next time you fly, remember, even in the rarest emergencies, Boeing jets are packed with layers of safety. Flying is safer than ever.